In 2012, NASA's Voyager 1 probe crossed the so-called helium pause, a vast bubble filled with electrically charged particles and magnetic fields that surround the Sun. It became the first spacecraft to enter interstellar space. Launched in 1977, Voyager 1 and its twin Voyager 2 have embarked on an awe-inspiring journey through space. As of 2023, Voyager 1 is hurtling towards the unknown at an astonishing speed of approximately 610,000 kilometers per hour, making it the fastest man-made object in space. Moreover, it holds the distinction of being the farthest man-made object from Earth, currently situated about 24 billion kilometers away. Light would take nearly 24 hours to traverse this vast distance. Throughout its voyage, Voyager 1 has soared past Jupiter and Saturn, ventured through the Kuiper Belt and the solar system's heliospheric boundary, and consistently relayed invaluable data back to Earth. Now in interstellar space, it's poised to encounter other star systems in its future journey. The first star Voyager 1 is projected to encounter after departing our solar system is AC plus 79 3888. While it might not have a familiar name like Sirius or Alpha Centauri, it's also known as Gliese 445. So what do we know about this star? Gliese 445 is situated 17.5 light-years from Earth in the constellation of Camelopardalis, often referred to as Giraffe. Interestingly, it's not within the constellation's visual pattern, but lies within its boundaries. Its nearest celestial neighbor is Polaris. Gliese 445 is a quintessential red dwarf, a category of stars that form the majority in our galaxy. Due to their faintness and small size, stars like Gliese 445 are only visible through telescopes. However, this dim luminosity contributes to the longevity of red dwarfs, which often outlive stars like our Sun. Remarkably, it's estimated that 20 out of the 30 closest stars to Earth are red dwarfs. The most luminous and closest red dwarf to the Sun is Proxima Centauri. Gliese 445's formation mirrors that of other main-sequence stars. Initially, a cloud of dust and gas was drawn together by gravitational forces, which then began to rotate. Over time, this material coalesced at the center. Upon reaching a critical temperature, fusion commenced. Typically, red dwarfs possess up to 50% of the Sun's mass, and that's their upper limit. In the case of Gliese 445, its mass is approximately 0.4 solar masses. The smaller stature of red dwarfs means they burn at cooler temperatures, with some reaching a peak of 3,220 degrees Celsius. Gliese 445's temperature is even lower. Their cooler nature results in a dimmer appearance, with some emitting light almost 10,000 times fainter than our Sun. Owing to their cooler temperatures, red dwarfs consume their hydrogen reserves at a leisurely pace. Unlike more massive stars that exhaust only the hydrogen in their cores before reaching their life's end, red dwarfs utilize all their hydrogen, both within and outside their cores. This slow consumption extends their lifespans to potentially 1 trillion years. Distinguishing between a red dwarf and another star type, the brown dwarf, can be challenging for scientists. Brown dwarfs are also cool and dim. Often termed failed stars, they don't sustain hydrogen fusion in their cores. To differentiate between the two, scientists measure the object's temperature. Brown dwarfs are even colder and possess significantly less mass. Chemical markers can also provide insights. The presence of compounds like methane or ammonia, which thrive at cooler temperatures, indicates a brown dwarf. Similarly, the detection of lithium in the atmosphere suggests a brown dwarf, as red dwarfs typically lack this element. Furthermore, many red dwarfs are accompanied by exoplanets. While massive gas giants akin to our Jupiter are uncommon around red dwarfs, their dimness makes it easier to detect exoplanets in their vicinity. making them prime targets for exoplanet hunters. Instruments like the Kepler Space Telescope, operational from 2009 to 2018, and the TESS Space Telescope, which commenced operations in 2018, have extensively studied red dwarfs in search of Earth-like exoplanets. Historically, scientists considered red dwarfs to be uninhabitable. Their limited light and heat meant that the habitable zone, an area where conditions might allow water to exist in liquid form, would be very close to the star. This proximity would expose any exoplanets to the star's radiation, which could be harmful to life. Some exoplanets might also be in tidal lock with their red dwarf, meaning one side perpetually faces the star, similar to how the Moon faces Earth. This would result in one side of the exoplanet being extremely hot, while the opposite side remains frigid. However, current research suggests that exoplanet systems around red dwarfs might still harbor potentially habitable worlds. In 2016, an exoplanet was discovered orbiting Proxima Centauri. Then, in 2019, astronomers identified another exoplanet orbiting beyond the red dwarf's habitable zone. The TRAPPIST-1 system boasts at least 7 exoplanets, and some studies suggest that a few might support life. The longevity and stability of red dwarfs make them intriguing candidates for hosting life-bearing exoplanets. Regarding our subject of interest, Gliese 445, no exoplanets have been detected yet, but absence of evidence isn't evidence of absence. While red dwarfs like Gliese 445 have impressively long lifespans, they, like all stars, will eventually exhaust their fuel. Their ultimate fate? Transforming into white dwarfs, the remnants of dead stars? Interestingly, our Sun shares this destiny. In essence, their stories converge at the end. To recap, red dwarfs are both the most prevalent and the longest-lived stars in our Milky Way. And it's towards one such red dwarf, Gliese 445, that Voyager 1 is speeding. However, reaching this destination will take time, about 40,272 years to be precise. The exact timeline depends on various factors, including the probe's trajectory and the star's motion. By that time, Voyager 1 will have ceased transmitting data and will be inactive. Remarkably, while Voyager 1 approaches, Gliese 445 is also moving towards our solar system. In 40,000 years, this star will be a mere 3.45 light-years away. For context, its current distance is just over 17.5 light-years. At present, Proxima Centauri holds the title of the Sun's closest neighbor. But as time progresses, this title will shift to Alpha Centauri, then to Ross 248, and eventually to Gliese 445. As for Voyager 1's fate after Gliese 445, it's projected to exit the Oort cloud in about 56,000 years. Subsequently, it will pass by stars GJ 686 and GJ 278 in approximately 570,000 years. By then, it will resemble a silent, man-made relic drifting through space. By 2025, all its instruments will have ceased functioning. But what of its sibling, Voyager 2? Voyager 2 is also journeying into interstellar space, albeit in a direction opposite to its twin. In around 40,000 years, it will approach the aforementioned star, Ross 248, another red dwarf located in the Andromeda constellation. This shouldn't be confused with the Andromeda Galaxy. In roughly 296,000 years, it will come within 4.3 light-years of the famed star Sirius. Predicting the ultimate destiny of the Voyager siblings is challenging. They might endlessly drift through the Milky Way or succumb to micrometeorite impacts or a significant collision. There's even a possibility that the Voyagers will outlast our solar system, and certainly their human creators. The question remains, will humanity endure until the year 41,272? Only time will tell.